In a television game show, contestants have to pass under a barrier. The barrier has a vertical height of 0.7 meters, as shown in the diagram, and moves up and down with simple harmonic motion. State the conditions which must be met for an object to move with simple harmonic motion. So for part A, it's just defining what simple harmonic motion is. That is when the restoring force is directly proportional to displacement, and it acts in the opposite direction towards equilibrium. The bottom edge of the barrier is initially in contact with the ground and moves up to a height of 2.3 meters before returning back to its starting position. The bottom edge of the barrier touches the ground every 4.5 seconds. A contestant requires a space at least 0.6 meters high to get under the barrier. Calculate the maximum time this contestant has to get under the barrier. So let's have a look at our diagram. So it says in the question that the barrier moves with simple harmonic motion. So that means that all parts of this barrier move with simple harmonic motion, as does this bottom edge here. It's easier if we just consider the motion of the bottom edge of the barrier, as this helps us to disregard the dimensions of the full thing. And it's that line that's important in this scenario. The contestant needs that bottom edge to be 0.6 meters above the ground for him to get underneath. So let's model its motion. It says in the text below that the bottom edge of the barrier moves up to a height of 2.3 meters before returning back to its starting position. So looking at our diagram, this makes sense. The bottom edge of the barrier cannot move through the full distance of 3 meters, as the rest of the barrier is in the way. This 0.7 meters of barrier is in the way. So the bottom edge will travel up to a distance of 3 minus the 0.7 meters from the ground before it returns. 3 minus 0.7 meters is 2.3 meters. That's where the 2.3 comes from. So let's draw this. So this is the vertical distance that the barrier's bottom edge moves through. Here is the equilibrium line. So it's a simple harmonic oscillator, meaning that it oscillates about some equilibrium position, which is always at the center of the oscillation. The distance above and below equilibrium that the barrier travels through is half of the 2.3, so 1.15 meters. Let's say the purple line represents the bottom edge of the barrier, and this black line represents the ground. We know the barrier is 0.6 meters above the ground. So it's 0.6 meters above the ground at that critical position where the contestant has enough space to get underneath. This means that the displacement from equilibrium, so this line here, the displacement from equilibrium would be the 1.15 meters minus the 0.6. That will be this distance here. So that will be 0.55 meters. Displacement is a vector, so let's consider the upwards direction to be positive. So our displacement would then be minus 0.55 from equilibrium. It's important to consider displacement from equilibrium, as our simple harmonic oscillator equations, such as the x is equal to a cos omega t, all consider displacement to be from equilibrium. So if we're trying to use those equations to work out what time is, we want to consider the displacement from equilibrium as opposed to from the ground. So when displacement is bigger than minus 0.55 meters, or in other words, when the barrier is above this position here, that's when the contestant can get under the barrier. We need to work out the time when the barrier is above this displacement. So we can pick sine or cos graphs to model this scenario and to help us work out when x is bigger than minus 0.55. Equally, there is nothing to stop us using negative cos or sine graphs. Let's have a look at these four to help us decide. So we have a sine graph, minus sine graph, minus cos graph. We know our simple harmonic oscillator has an amplitude of 1.15 meters. These graphs show the displacement from equilibrium or the middle position. We could technically use any of these graphs, but some help us visualize the situation better than others. Again, we're trying to see when x is bigger than minus 0.55. So I'll highlight these regions. So these orange regions here are where x is bigger than minus 0.55, which is, again, where the bottom of the barrier is above 0.6 meters from the ground. The negative cos graph is the only one where we have a continuous orange line. And we can really imagine what's happening from the person's perspective using this graph. The barrier starts on the ground and then rises to when it is 0.6 meters above the ground, when the displacement from equilibrium is minus 0.55, and the contestant can then get underneath. He has this whole chunk of time here, when the barrier is above minus 0.55 from equilibrium, to get underneath the barrier. So we need to work out this time. Let's write our full equation for displacement now. So our equation would be x is equal to minus a cos omega t. So you're used to seeing x is equal to a cos omega t. We're putting the minus sign in front because we have a reflection of a cos graph. This is a negative cos graph. We know that the amplitude is 1.15 meters. Omega is 2 pi over time period, and the time period in this case is 4.5 seconds. The bottom edge of the barrier touches the ground every 4.5 seconds. So that is omega. And we're trying to work out when x is equal to minus 0.55, we're trying to work out what times will we get for that displacement. So let's have a look at our graph. So when x is equal to minus 0.55 meters, when we put that in our equation, we can work out what these two times here are. We then find the difference between those two times. That will give us the time that the barrier is above 0.6 meters from the ground. That will be our answer. So we have minus 0.55 is equal to minus 1.15 cos omega t. I'll replace the omega later with the 2 pi over 4.5. So then cos omega t is equal to minus 0.55 over minus 1.15. If we do inverse cos of the right-hand side of that equation, so inverse cos of this, that gives us 1.0721. And then we can divide that by the omega. So do the 1.0721 all over omega, which again is 2 pi over 4.5, and that gives us 0.7679 seconds. So that would correspond to this time over here. I'll just round it to 2 decimal places, 0.77. We know the time period of our scenario is 4.5 seconds. We know that. So that means that this time over here, the full oscillation takes 4.5 seconds. And because a cos graph is symmetrical about this line here, if this time interval is 0.77 seconds, this time interval will be 0.77 seconds as well. So if we do 4.5 minus 0.77, that gives us this time here. So that will be 4.5 minus the 0.7679. That gives us 3.7321. So that will be this time, 3.73 seconds. And now we find the difference between this time and this time to get our answer. So 3.7321 minus 0.7679, and that gives us 2.9642, 2.96 seconds. That is the time that the contestant has to get under the barrier.